So today we're going to be going over what vectors are and the different properties of vectors and the operations that we can perform on vectors. Both very simple operations and slightly more complicated operations. So to understand what vectors are, let's first look at what simple numbers are. Numbers are used to represent a value. When I say, and usually we represent numbers on a number line. That's 0, that's negative infinity, that's positive infinity. So we simply use numbers to represent a value, a magnitude of, let's say, a force of 5 newtons. That could be represented by a simple number. But in the case of a force, there's also another thing. And that's where we require the use of vectors. Because a force, let's say I draw a force of 5 newtons. Sure, the magnitude of this force can be defined using a single number, that's 5. However, a force is this 5 Newton force, this one which I just drew, this 5 Newton force, is different from this 5 Newton force. It's a different force. The red 5 Newton force and the green 5 Newton force are different forces. Now, if we just use numbers, we can't find the difference. We can't define the difference between two different forces. That's because numbers only represent a single value. They do not represent a direction. Vectors are sets of numbers. They're not a single number, they're sets of numbers. And you might say, well, what sets of numbers can define this 5 Newton? And we can say 3 and 4. And this 3 and 4, we would usually not use just a number line, but we'd use a x and y plane or a x, y, and z plane. For 2D and 3D vectors, this would be a two-dimensional picture. And we'd say you travel 4 here, you travel 4 across, and 4 across, probably across, 3 upwards, and there you have your 5 newtons. And then you would have your angle as well. So vectors are sets of numbers used to represent magnitude and direction. Also, I'd like to note that this is a very simplistic understanding of numbers, and the only reason I went with this explanation of numbers is so that I could explain what vectors are as a set of numbers that define magnitude and direction. There are two properties of vectors. One, that of magnitude, and this is the notation used, these two long bars. If A is a vector, and let's just, I guess, draw A, let's use the same example, 5 newtons. That's our A vector. There's a magnitude, and there's the argument, usually denoted as arg of A. Now the magnitude is found by the square root of the distance moved in the x direction and the distance moved in the y direction, x squared plus y squared. Now from elementary math, or I guess secondary math, you guys would probably have learned the Pythagoras theorem. So if we have this side C and we have these sides A and B, I'm sure you can already try and see the relationship between the Pythagoras theorem and finding a magnitude. We find the length of C using the Pythagoras theorem. C equals square root of A squared plus B squared. This here is nothing but the Pythagoras theorem in action. And the angle, when we talk about the angle, we mean this angle here, or rather this angle here, because that's our actual force. And the way we find the argument is by thinking about SOHCAHTOA, sine, cos, and tan. Here we'd use tan because the idea is that we don't have the force, but we have x and y. So the argument would be tan inverse of opposite, which is y, opposite of the angle, over x. That's how it would go. So these are the two properties of vectors, magnitude and argument, and are rather quite simple. However, in the argument part, when we have, let's say, a force like this, and we have to find the angle like this, we have to think about what value tan theta will give us, and then subtract it from 180 or from 360 or whatever, so on and so forth. That's more the maths of it, and I'd hope that you know that from your previous years. Or perhaps I can try and go over that in some other video. Now let's come to some basic operations. The basic BODMAS operations, I guess just DMAS, do apply to vectors, which is addition, subtraction, and multiplication, division. I know you got the point. I'm not really sure why I wrote them down. And addition and subtraction of vectors is very, very simple. Multiplication of division is slightly more difficult, but I've never really ever seen multiplication and division being used. So I won't really go over multiplication and division. I'm now in university and we have gone over vectors, and they never even talked about multiplication and division of vectors. So I'm not really sure if it's relevant to learning for an exam at least. If you're interested, of course, go ahead and employ your time wisely. But let's just go over addition and subtraction, the common operations. Let's say if A is 2, 1. By the way, I should probably go over how we denote or how we represent vectors as well, different ways of representing vectors. One is a column vector, so we go x, y, and let's say we have another plane z. By the way, this is how it would look. This is how three-dimensional vectors would look. Let's see, if this is x, this is y, this is z. That's how three-dimensional vectors would look. We'd go across x, right? Then we'd go along y, and then we'd go higher up or down the z-axis, and that's how we would find our new vector. So this is a notation, or you could just put it down as a set of coordinates x, y, z, and these are really the only two notations that probably will be used. So let's say we have a vector 2, 1 and a vector -3, 5. So when we add them up, that's just 2 minus 3, which is -1, and 1 plus 5, which is 6, and that's just the addition of two vectors, a and b, a being this, b being that. This is rather simple enough, and I'm sure you can figure out how subtraction would work as well. If this was subtraction, we would just subtract. It would be 2 minus 3, so 2 plus 3 and 5 minus 1. Now coming to two rather advanced operations, that of the dot product, and far more practical as well, and cross product, the more complicated of the two. So let's first start off with the dot product, because it's really simpler and usually people start off with the dot product. So what the dot product does is project, I'm not really sure I like this language, but that's what it says, project one vector onto another. And there's another way to think about this as well. But let's first really try and understand what the hell is going on. Project one vector onto another. Let's say I have a vector A. Alright, fair enough. And I have a vector B. So convenience on the x-axis. But the x-axis is not drawn correctly. There we go. That's much better. Why the hell is this tick error? So when we say project one vector onto another, what we're trying to say is how similar is A with B. How similar are both of these? A dot B is the notation for a dot product. Also to note, it's the same as B dot A. So you can think about how similar is A, or how will I, if I project A onto B, what would the result be? How similar are these two vectors? How similar is A to B or B to A? The answer will be the same. How similar, or we can define this as how similar two vectors are. And that's all well and good. But what's really powerful is that we have a formula for what a dot product is. So it's A dot B equals the magnitude of A, so the length of this vector A, the magnitude of B, the length of this vector B, and I hope you remember what magnitude was from before and how we calculate magnitude using the Pythagoras theorem. That is very useful. And cos theta. Now cos theta, what the hell is that? Well, that's the theta. That's the cost of this theta there. And now you might say, well, that's all well and good. There's a formula, but what the hell? What do we do with it? How do we even do this dot product thing? We only have known addition, subtraction, multiplication, and division and stuff. So what is this dot product? Well, it's rather very simple. Let's say you have a vector x, y, z, and a b vector x1, y1, z1. The dot product of both of these is as simple as just writing them down in their column vector forms together. That really helps do it. I guess you could do it directly as well if you really want it, but this simplifies it for me. And we multiply the x and the x, the y and the y, and z and the z, and we just sum them all up. So x1 plus y1 plus z1. And there's no particular reason why I wrote it down in a column as opposed to writing addition there. There's no particular reason for that. It's just that, that line was there, didn't really want to cross it. And that's how you take a dot product. If I were to show that with real numbers, 1 to 1, and I'm going to go really fast with this, I hope, 3, 5, 3, wow, 3 plus 10 plus 3. So you should be able to see that you will actually just, in the end, be adding all of these, giving us 16. It won't be x is separate, y separate, and z separate. So that's how we take out the dot product, and the magnitude of the dot product would just really be the dot product. I guess I could remove this, there's no point. And you could then equate it with the magnitude of A, the magnitude of B, and the angle between A and B, which hopefully you never have to calculate. Hopefully. And you might now say, fair enough, I understand what the dot product is, abstractly, slightly. I understand the formula, I understand how to take out the dot product, but why? Alright, fair enough, but this is physics. It's supposed to be more practical than not. I'd hope it's supposed to be practical, but it's not always. So what practically can we do with a dot product? And there are a couple of things. One very basic is finding, wait a second, wow, practical. We can find work done. Now let's say we have a box which I'm representing as a dot, and there's a and it has moved this much distance, moved this much displacement, to be accurate, to be honest. Let's say a displacement of 10 meters. And there's a force acting on it of 7 newtons. Now, how much of these 7 newtons is actually acting parallel? Parallel. Very important word here. How much of this force is acting parallel to this displacement D? Well, if we figure that out, that will essentially be the work done. If we figure that out and then multiply that with the displacement, that would be work done. So we can resolve this vector. We can resolve this. Resolve meaning if we have been given the angle, we can find out how much of this is the x coordinates, and how much is this is the y. We can try and figure that out. But the power we have bestowed upon us through the knowledge of dot products is simply, we can apply the dot product here. We can say that this force dot this displacement would be the work done. Very, very simple stuff. And that's how we'd use a dot product. This is one application of a dot product. I'm sure you can think of all the other places where the distance or the displacement is parallel to the force or some other scenario. The cross product, now let's coming to the cross product, is slightly more confusing, and that's why most people, I guess I shouldn't speak for most people, I do not like the cross product that much. So the cross product is the area of the parallelogram, bear with me, formed by the projection of the two vectors. Now let me, before trying to explain anything, draw out what exactly I mean. We have again this vector b conveniently on the x-axis, and we have this vector a. Now, I hope you can see this the first time. This is parallel to A, which I'm calling the projection of A. And this is parallel to B, which I'm calling the projection of B. Now, the area that's in this parallelogram is the area we're talking about. It's also important to note that this is all mostly about rotation. How much can A rotate onto B, not R, and how much can B rotate onto A. These are actually different. The notation is A cross B for a cross product is not equals B cross A. They're not the same thing. And if you calculate A cross B and B cross A, you'll instantly find out that they're not necessarily the same. An important thing to note, and this should clarify a couple of things, I guess, is the cross product, is maximum when two vectors are perpendicular to each other. So in our dot product case, they would be minimum if they were they would actually probably be 0. Yeah, they would be 0 if they were perpendicular, and maximum when they were parallel. A dot B, I mean. But here is the opposite case. When the two vectors are perpendicular, that's when A cross B is maximum. Now that's all well and good, but where's the formula? And here is the simple formula. A cross B equals magnitude of A, magnitude of B, sine theta. Not cos this time, sine theta. I'm sure there's some divine mathematical reasoning as to why it's sine and cos. It's probably pretty simple, but let's just get on with it. So that's the cross product. Alright, that's nice. So how do we take out a cross product of a 2D vector? What the hell was that? I really hope I did not lose all of my work. Alright, there we go. That took like a couple of seconds. So 2D vectors. And it's harder to do it for 3D, that's why I'm going over 2D first, then I'll also go over 3D. In the dot product there was no need at all. So a 2D vector, let's say A is 2, 1 and B is 3, 5. Here, by the way, I should also go over this notation, perhaps I should have gone over it before. The notation of I, J, and K. I being the unit vector, meaning a vector of 1 magnitude. That's what a unit vector is. Or rather, let me go to the introduction and show you guys there what I mean by IJK. This is a really important concept for cross products. So even if I did teach you earlier, you wouldn't really get why the hell that was being taught. So a unit vector is when the magnitude of a vector is 1. I, J, and K are unit vectors, which are, by the way, denoted as a hat. That would be the unit vector of A. So I, J, K are unit vectors in x-axis, y-axis, and z-axis. So that's simply what IJK is. So instead of, just saying x, y, and z, what we could say is here's your I, that's your I direction, that's your J direction, and that's your K direction. So we could say that. Then if you're going higher than 1, that would be, let's say, for example, 5K. Higher than 1J, that would be 11J. More than 1I, or less than 1I, 0.5I, or minus 10I. So that's how we'd vary our vectors in the IJK representation. That is also a valid representation. Coming back to cross product, really quickly, A cross B, we'd line up the I's and the J's. So we'd line up 2 and 3. They're both I coordinates, 2 and 3. And we'd line up 1 and 5. So this would become our A and this would become our B. And what we do with them is also rather simple. We multiply I of A and J of B, and we multiply 1 and 3, so 2 times 5, 10, and 1 times 3 is 3, and we always subtract, no matter what, we subtract both of these, so 10 minus 3 is 7. Now what I mean by always is that, let's say this was minus 1, we would get 10 minus 3, we would still subtract here. So by subtraction, I don't mean that I would ignore this and make it a plus. No, what I mean is that we would subtract minus 3 away from 10, which is the same thing as 10 plus 3, 13. That's simple enough with 2D vectors. With 3D vectors, let's say we have a 3D vector. A is 1, 2, 1. B is 6, 4, 2. So we again line up I, J's, and K's. I's would be 1, 6, 2, 4, and 1, 2. I hope I got that right. And now, here what we do is first find for I, and when we're trying to find for I, we ignore I completely, and we just continue with our determinant. I'm pretty sure we call this the determinant when we cross multiply like that and subtract. So 2 times 2 is 4, minus 4. Wow, there is no I. That's interesting. Once we're done with the I, we repeat the same thing with the j, but there's something else that we always subtract. We always do minus j. No matter what, we always do minus j. Minus j, and j would be in this situation 4 minus 2 times 6, which is 12. So we did get a negative number here, so this minus and the negative number would become plus, but that's for later on. And then the same thing with k, and for k also we'd ignore k. Sorry, I believe I did it wrong for j, because I did not ignore j there, which is actually very important and a pretty common mistake, common for me, but I'd hope for others as well, that we might forget one of these vectors, well, I, j, or k. So let's ignore j, so it's 1 times 2 minus 1 times 6 minus 6, there we go. And then we ignore k, and that would be, damn it, I don't remember what it was. That was what, 4 minus 12, right? That was simple. So this would become 0i. We wouldn't write 0i, we'd just not write anything. Plus 12j minus 8k. So 12j minus 8k would be our cross product of these two vectors. It is also important to understand, or mostly remember, these couple of things. I really didn't know what to call these. I cross j is k. So this is when you take the unit vector of x-axis and the unit vector of j-axis. What we get is a vector in the direction of the k-axis. And j cross k is I, and I cross k is minus j, and j cross I is minus k, and k cross j is minus I, and k cross I is j. That was a whole lot to take in. This should slightly make sense, that if we flip I and j, we don't get k, we get minus k, and pattern follows. And that's all well and good. I hope you understand the formula a bit better. You understand how to take out the cross product. You understand abstractly what the cross product is telling us. But hey, what gives? Where's the practical use of a vector? Well, we can think about torque. We can think about torque on toolbar or something. Toolbar? What the hell is a toolbar? A spanner. Let's just say a spanner. Torque on a spanner. So we'll be applying some force here. And let's say, for the sake of argument, that this force is not perpendicular. So that's this force here. And this is the displacement. Torque or moment, whatever you want to call it. I'm not really sure what the exact difference is. This is your displacement d. So in this case, what we're looking for is what part of this force in the y direction. Well, we'd resolve for the y direction, and we multiply that with the distance, because for moments it's about perpendicular distance. It's not parallel. In the dot product was parallel, here is perpendicular. So what we do simply is, instead of resolving, take out the cross product. Let's say the torque, I guess we meant with moments. So let's just say M equals F cross D. And that's how we'd find the moment present on this vector. So that's all for today. I hope this video was helpful.